Hey folks, in this video we'll talk about limits that involve the symbol infinity. So here are some goals for the video and some things that I'd like you to be able to do when you're done. So to start, what do we mean when we write something like this? Well, let's start with the symbol at the bottom, this X and the arrow going towards the infinity symbol. When we read that, we might say something like X approaches infinity, but infinity is not a number. X can't get close to it. Really, what we mean is just that X is growing and growing and growing and not stopping. So to say that the limit of f of x as x approaches infinity equals some number L, we mean that, well, as x gets bigger and bigger and bigger, the value of f, the y value, is just getting close to and staying close to L. Let's look at some examples and their graphs. So here we'll look at a couple functions and their behavior as x goes off to infinity. So first, this function in green is f of x. And you can see that as x gets larger, it seems to approach the line y equals 2. In fact, let's put that line in here. And yeah, you can see they get closer and closer. Maybe we'll look at a table of values. We don't need any small values. And we can see that for bigger and bigger values of x, that the output f of x just gets closer and closer to 2. Now this isn't a proof, but it demonstrates the point. What about this function g of x? Zoom out here. So here we see g of x is sort of this dampened sine function. So it's oscillating back and forth, but getting flatter and flatter. That is, the amplitude is getting flatter. And as we move to the right, it's getting closer to the x-axis. We can check a table of values. We'll do the same. And you see it's bouncing between positive and negative values, but in terms of the magnitude or the absolute value, they are getting smaller and smaller. So I wanted you to see this example. Often when we think about things like this, we imagine our function not crossing the line where the limit is equal to, getting close to but never equaling. That doesn't have to be the case here. This crosses the x-axis, the line y equals 0, infinitely many times as it gets closer and closer to sort of settling there. So to help us deal with some limits as x approaches infinity, we'll isolate two important basic cases. That is, what these limits look like, that is x to the n, and 1 over x to the n, where n is any positive number. Well, in the first case, if we've got x to the n and n is going off to infinity, then this value is infinite. It's getting larger and larger. So we can say that the limit equals infinity, or we can say that it does not exist. Either one is a correct thing to say. And a graph of a function like this might look this way. On the other hand, if we have 1 over x to the n, well, as the bottom of this fraction gets larger and larger, the fraction itself is getting smaller and smaller. So this limit is going to 0. And the graph might look something like this. So let's see how we can use these two facts. We'll take a look at this function we just saw. We know the answer is that there is a limit of 2 as x goes off to infinity, but I'll show you how we can discover this algebraically. Now, I recognize here that the highest power of x that shows up is a squared, a power of 2. So I will divide the top and the bottom of this fraction by x squared. And term by term, I can rewrite it this way. And the reason this is helpful is now every term looks like that second fact I just showed you above. Either it's a number like 2, which doesn't change as x goes off to infinity, or it's a whole term that vanishes, that goes off to 0 as we take this limit. So now when we take the limit as x goes to infinity, we can cross out 3 of the 5 terms, and we're left with just 2 over 1, or 2. And we see why this is our answer. So we'll leave off with a definition. This is a term you probably are familiar with, but maybe you haven't thought about it this way. We say that a function f has a horizontal asymptote at the line y equals L if the limit as x goes to infinity of f is equal to L. And this works for minus infinity also. So here we're sort of talking about the end behavior of a function, what's happening way off on the x-axis. So if a question asks us to identify any horizontal asymptotes, well, there are 2 places to look. We can look off to the right as x goes to infinity, and off to the left as x goes to minus infinity. So we can take 2 limits and find any or both horizontal asymptotes. Now, what do we mean when we write something like this? The limit as x goes to a of f of x equals infinity? Well, we certainly don't mean that the value of f is infinite. That's nonsense. Remember, infinity is not a number, it's a concept. So rather than saying the limit is infinity or that f equals infinity, it's more correct to say that f approaches infinity. And really what we mean is that as x gets larger and as x approaches this value a, the function f gets larger and larger, either in the positive direction or in the negative direction. And there are some subtleties here that we'll see. Let's take a look at GeoGebra for some examples. And in this example, we see this function f of x again. But the question is, what happens when x gets close to 0? Well, we see it depends on the direction. As x approaches 0 from the right, our function is getting bigger and bigger. It never equals 0. That is, the input never equals 0. That would give us a 0 in the denominator. And we see the function just grows and grows. From the left, the y value grows and grows in the negative direction, getting close to the y-axis, but again, never crossing it because x equals 0 is not in the domain of this function. So we've got an infinite limit as x goes to 0 from the right, and a negative infinite limit as x goes to 0 from the left. In one of these examples, we saw the limit of this function, and that at the point x equals 0, there were 2 things going on. From the right, we saw that that f was going up to positive infinity, whereas from the left, f was going down to negative infinity. So hopefully that was easy to see from the graph, but how could we talk about that algebraically, just looking at the function? Well, I'll give you a fact that we can use. If the top of a fraction, as we approach some value, is just approaching a real number that's not 0, but the bottom is getting close to 0, that is, we're getting close to dividing by 0 while the top is not 0, then there's some infinite behavior here. Our function is either getting infinitely large in the positive direction or in the negative direction. And there's a little art to figuring out which one it is. So if it looks like we're dividing a non-zero number by 0, something infinite is happening, but we need to figure it out. And I'll show you by example. Let's look at this function again, but I want to know what's happening around the point where x is -1. So let's see that those two criteria are met. Here at the top of this function, of this fraction, if we plug in -1, we see that it's going to 9. That's certainly not 0. But, well, especially after we factor, you can see the bottom of this function is getting close to 0. If you were to plug in -1, the bottom would be 0. So we've got some sort of infinite behavior, but let's parse it and see in which direction. And it turns out it's both. And we need to figure out from the right or from the left which is which. So we'll look at these two factors and ask, well, if x is bigger than -1, that is, if we're approaching -1 from the right on the number line, then, and we're close to -1, well, then x itself is close to -1, so it's a negative number, and x plus 1, well, then this would be bigger than -1. This would be slightly bigger than 0. A negative times a positive is a negative number. And so 9 over a negative number is negative. We would have a negative infinity limit as x approaches -1 from the right. And, well, if x is less than -1, then certainly x is negative. And as x plus 1, as x approaches -1, x plus 1 is still negative. It's getting closer to 0, but still negative. So maybe let's take a look and see this pan out in GeoGebra. So here, one last time, is this function f of x. I've added in the vertical line x equals -1. And you can see that, yes, as x goes to -1 from the right, our function seems to be dipping off to -infinity, whereas as x goes to as x goes to -1 from the left, our function value, our y value, is going up to positive infinity, just like we saw. So a final definition, again, this is a term you've used before probably, but we say that a function f has a vertical asymptote at a point x equals a if the limit as x goes to a is equal to infinity. And this could be the limit as x goes to a from the right, or from the left, or both. It could be positive infinity or -infinity. So if a question asks us to identify any vertical asymptotes, we need to figure out, well, maybe where the denominator is going to 0, and then we can evaluate those from the left and from the right to see if we've got infinite behavior.